And I'll switch to the presentation. Okay. Everybody sees the slide, the PowerPoint? Quick thumbs up. I just want to make sure that I'm sharing the right screen. Okay, thank you. In this part of the class today, I'll talk about GANs, the Generative Adversarial Networks. This was something that originally was planned for tomorrow, but we'll be demonstrating tomorrow these concepts again. So we'll kind of introduce the theory today and see more of the practice tomorrow. So what are the generative adversarial networks? These are generative models par excellence, that's in the name. And they're based on this kind of easy to understand, surprisingly powerful idea that instead of having labeled data in some sense, or knowing what you want to generate, or doing some sort of an auto-encoding, we can substitute our teacher with something that is actually is trained together with the network. And so what does that mean? In this kind of a pictorial representation, and we have some random source, right? So these bits and pieces, kind of a random inspiration that allows the generator or the forger to generate an image. Now, he is trained to generate images in a very specific style. He doesn't really try to forge Mona Lisa, but he can forge a lot of pictures that are in the style of Mona Lisa. Now, what the detective has to do is he has to basically judge an image that the generator created, the forger, and say if it looks authentic to him. He doesn't really want to detect Mona Lisa, that will be a very specific case. But if there was a whole set of Renaissance paintings, I don't know if by Leonardo da Vinci or anybody, and now he finds a new painting that somebody brings to him, he has to judge if this was a fake or this really belongs to that set. And there is no real reason to believe that somebody today cannot fake a Renaissance painting. So the idea is that, yeah, I mean, probably there is a generator and it can create more images. And these images will be kind of inspired by some random noise that goes through the generator. So we will be training basically two things together. We'll be training the detective. So the detective will slowly try to improve his skills and try to see if he can actually find little details that distinguish the real data from the forged data. And every time he rejects an image, the forger or the generator gets feedback, and then he tries harder to basically imitate or improve his style so that will be undistinguishable. And at a certain point, they will basically get to some kind of an equilibrium where the detective will not be able to distinguish these things, and the forger will basically end his training by generating as best as he can. So how is that formulated a little bit more mathematically? We deal here with three different distributions. One, we have that noise that we spoke about, that is the source of all inspiration. We have the generator distribution over data. So again, we model this as a conditional distribution that takes this Z prior and generates data, okay? And then we have the real data, which we again treat as a probability distribution. This is why we always work with big data. We work with a corpus of examples. So every picture, basically, every collection of paint dots or pixels or stains on canvas is X, but the way we define the collection of Renaissance paintings is that they have to be very particular, shaped and used, and so the probability of seeing different pixels is what defines our data. Again, conceptually, kind of surprising that this idea of probability can be extended as far as really modeling, like musical style or artistic style, but apparently it works. So if this looks weird to you to think about style as basically probability over the domain of whatever media you're generating, and Renaissance is just a probability over all paintings, or Bach's chorales are a probability over notes for all possible musical random keystrokes. That's kind of the game we're playing here. So we have the real data probability, we have the generated probability, and basically here, because it starts with this randomness. So this is kind of like the decoder in variational autoencoder, right? Variational autoencoder has this prior, I mean, in variational autoencoder, there is this prior that goes through this network that we learned, and then through a mapping. So here it's everything inside. You start really with the Gaussian. So if there is an element here that generates, shifts the mean and changes the correlations between these Z's, and then also maps this to the image domain, all in the generator network. But you just plug this into this sufficiently elaborated network, and you hope that this black box will be eventually tuned to generate something by defining this this scheme, this adversarial, and it's really an adversarial. It's like a game. And so here you have another network also being learned, the discriminator, and what the discriminator receives is either examples of real data or the generated data. The supervision for the discriminator is that since you know how you switch the examples. I mean, there is a little switch here. You either give it a true example or generated example, and whenever it's true, you know what should be the answer, or whenever it's fake, you know what should be the answer. And basically it does learn in a supervised way, but this labeling is very simple, right? You decide which example you provide, so you know what should be the answer, and this gives us the feedback or the error function to train the discriminator. So this kind of learning can be expressed as a loss function with these two competing requirements. So how they're expressed mathematically here, one is that we have, we generate the real data, okay? So X is distributed from the real, the PR, the data distribution, this one. And we have some, the discriminator, and we want, here we have this kind of min-max. We want to maximize this log of D. So whenever we have a real example, we'll have log of D. So D will be positive, so we'll have a positive answer here. If it's generated from the fake examples, okay, then we basically have the generator that takes Z and creates a fake image. So we want this to be judged as 0. So this is expressed as 1 minus, okay? So in this setting, we want to maximize this loss function with respect to the discriminator, okay? While on the other hand, we want to minimize this function for the generator, because the generator actually wants the discriminator to fail. He wants the discriminator to give an opposite answer. So discriminator, so the generator actually exists only here. So we see that we have these two different, some of these two different expectations or losses. Each one is averaged on a different set of data, pulling from here or pulling from here or from here, and then translating this here. And we can train separately the discriminator that appears in these two equations, or separately the generator that exists only here. The other element just to consider here is that, we can switch this is distribution over Z. If we look at the generator here, we basically write this directly as a generator, but again, these are different x's. This x is the true one, and this x is the fake one, okay? So I will not go through this is just excerpt from the original GAN paper, but it kind of shows that you split this into these two different updates, okay, two different steps of updating the discriminator by ascending stochastic gradient, or update the generator by descending its stochastic gradient. So because of this min-max or this adversarial game, you actually have to go through these two phases of training. And mathematically, this kind of leads to some idea of where it could land. I mean, why this model actually converges to something reasonable. So I want to kind of point out what are the optimal solutions for this setting. Since I do not have anything I can see right now, I hope also how I'm doing in terms of time. I might switch in and out from the presentation just to make sure that we are not going over time. So this is our original loss, okay, expressed as these expectations. And the reason we use x is just so we can have the same variable to use in both cases. But here is the probabilities of all possible images or sounds weighted by the true data, and here is weighted by the generated data. So, I mean, once we kind of look in here and forget about this being generating here, it just kind of allows us just to write this mathematically more elegant. But that's kind of the idea here. So now let's say we want to optimize on the discriminator. So we basically try to find at the point where the derivative according to this discriminator is 0, right? So that will be our extrema point. We kind of plug this into the integral and want every moment here to be 0, or for every x, if you want this to be 0, we get to this expression. Okay, I will let you kind of just verify the math. So it shows that the optimal discriminator basically will converge to this sort of a ratio of probabilities. And ideally, that means that the discriminator error will be 1/2, because if the PG equals P data, or, well, here we use data and R are the same. So it shows, I mean, that this duplicate notation also was in the previous slide. So PR and P data are the same thing. So if PG and PR, PG and P data are the same, then basically you have P divided by 2 times P, you have 1/2. That means in the best case, the discriminator will have a loss of 1/2, which means he will randomly have to decide whether an example is true or false. And that kind of attests to his lack of any better ability to discriminate. If all he knows is that there is a chance that something comes from the true exam, true set of, there are no priors here. So you assume that the size of the images generated by the true examples and the amount of images generated by the fake are the same. So all he knows is that there is a probability of 50% that somebody basically gave him a fake image, but that's the best he can do because he cannot distinguish any better. Now, if the discriminator is trained to this extent, then assuming that we reach the optimal solution, and this is a big assumption because in practice this doesn't necessarily happen when this whole mechanism collapses. But if we do manage to train it and we're getting close to this, then at that optimal point, the generator, we just plug in this here, okay? We can kind of play here a little bit with definitions or with math and see that what we have here is P data times log P data divided by the sum. If we want to rewrite this instead of this way as P data plus PG divided by 2, what we'll have is a KL expression between your data and so-called the mean source or the average source. In some sense, this distribution tells you that if we can generate something with probability for the data and probability for the fake, and this is kind of the average thing. So we kind of like randomly choose with probability 1/2 between these two. We'll call this our common, or just trying to recall what's the right exact terminology in statistics. The joint source. This is the joint source. So so what we compare here is the KL distance, or Kublik-Liable distance, the statistical measure between your data and the joint source. And here is between your fake data and the joint source. Each one of these, once you do that, I mean, this expression where you take your data and compare it to the joint source, and you take your other data and compare it to the joint source, this sum together divided by 2 is called Shannon distance. It's quite a known distance, and exactly that's what it does. The distance between R and G will be distance between R and the common source and G and the common source. And the reason for the JS distance is that it's symmetric. It has some nice properties, and it's a little bit more intuitive than KL. KL itself is not symmetric distance. So once you get kind of to play around with these KL distances, and in this course and later courses, you kind of can understand that it has some issues, the fact that it's not symmetric. But the reason I say that, really, you can see that at the optimal distribution, what we get is that the loss function becomes this symmetrical loss function. And of course, it will be 0 if R equals G. Okay. So, and this 2 log 2 is just an extra math here because of putting this 2 here and switching between these definitions. Again, I don't want to go through the algebra, but believe me that this is just kind of a straightforward derivation. And so why I'm showing all of that? Because this is what kind of proves that if we do manage to get to the optimal solution, the discriminator will be having basically hard time, will have nothing better than probability 1/2 to distinguish between true or fake. And in this case, if we want to minimize this, the probability of the real images versus the probability of generated images will be 0. So if you manage to now to basically lower this, or we optimize, I mean, the lower limit of this loss function will be 0, and in this case, the fake here will be exactly the same as the true. So ideally, if everything works, we'll come to this situation where we can imitate the true distribution by generating it. And in the process, we basically train both the discriminator and the generator. There are many known problems with training GANs. So one is so-called model collapse, where the training tends to be stuck in a small subspace. So there's an example of generating, I think these were like bedroom images, and you know, then when you keep generating more images, they tend very much to repeat themselves. You don't get all the variety of the original data, and somehow the network kind of comes to the point of being able to generate only few images very correctly. And so if all you learn is to forge something like a Mona Lisa, so you can reproduce the Mona Lisa perfectly, but you will not be able to forge new paintings by Leonardo da Vinci, right? So you will not have this new discovery anymore. You can just create a forgery of an exact example or a very small set of these images. So this is kind of a model collapse. It's mode collapse, not model. I have to create mode collapse because from all the modes in the probability, you kind of just stuck to learning a very small subspace of probabilities, mode collapse. And the usual training problems are that if the discriminator behaves badly, the generator doesn't have accurate feedback, so the loss function is basically doesn't do its job. On the other hand, if the discriminator is doing too good of a job, okay, then the gradient of the loss function will be very close to zero. So it becomes very slow for the generator to learn or improve itself. Why then GANs are became so popular? First, because I think the idea is really neat. It's one of the best inventions since what is it? It's the cheesecake. I think that's what Jan Lekman said about it. And then you can also kind of use this logic, this idea, to have totally new applications. And one is so-called pix-to-pix. So what is pix-to-pix? The idea, for instance, here is to be able to sketch this shoe and have the generator, so you sketch a shoe, and you have the generator basically create a photorealistic image of that shoe, okay? Or you give some kind of a sketch of, I don't know, you give the chords here and you get the actual notes, okay? You give some sort of a black and white image and you get a colored image. So you have a generator that actually does something or completes the data from very partial representation, lossy representation here. And then, instead of detecting whether this is a true shoe or generated shoe, what you do, you provide pairs. So the task is slightly modified. What the discriminator should tell you is whether this pair is legit or not, which means, is this image? And in this case, how would you generate these pairs? Well, in this case, you can maybe use some kind of a line or edges finding algorithm, right, on an image to create a contour. So you basically have a lot of true examples, and you have now sketches that are completed into images. If these are colored images, right, so you have the original colored image, you make it black and white, and this is a true pair, then you take a new black and white and you want it to be colored. So you can kind of, with some manipulation, or you have music recordings and you have some kind of chroma vector, right, or extraction of partial representation. But this is a true pair because you had an algorithm to actually create this for you. So this is a true pair, or you give just that partial representation. You don't have the real data, it will generate the real data. This is the learning example. So if this is generated, this is fake, but this was the real one, and eventually you will train it in the same way. And if you haven't, I don't know how we're doing in terms of time, that's one of the issues. Just try out this online pix-to-pix example. You can sketch a cat and you get an image of a cat. So another example is super resolution. So you can basically learn to take a low quality. So this is kind of trying to solve this rate distortion problem, right? You have a loss, you have a very compact representation, but also with some loss. And you learn the task of the generator is not to generate an image, it's to generate smooth interpolations locally. So you'll get a high resolution image. I hope you can see this in the video. I mean, this is really pixelated. This is the fake one. This is the true one. This is still sharper, but and this is one of the typical applications. And the way it's translated to GAN is that you have basically a low resolution image, and the generator is supposed to create this super resolution or high resolution, and you have the true high resolution image, and you, again, it's exactly the same setting. You can basically switch between generated images or the super resolution interpolated images and the true high resolution, and the discriminator will basically learn which one it is, and you have the GAN loss, and it's the same, exactly the same setting. Music applications, before we run out of time. Again, one of the good sources to go, because the Magenta team, the Google, have been very active in this domain. It doesn't mean that there's like tons of other research labs and publications that do these things, but somehow Google is the place to go, at least if you want to convince people that this is an actual practical problem. I have no idea what Google plans are about taking over the musical world, but the fact is that either they can allow themselves to work on this, or they can have some kind of idea why a commercial company would want to do these tools. I haven't seen any product that they're trying to market with either synthesis or music composition, but GANs is one example. And we can see, let me just play a few examples, because I think I'm running out of time, and you can check this out. In this case, what they do is they kind of use, this is one of the more recent works. They had the neural hints, which was an earlier work also using neural network, but this one is using GANs. So this is from last year's ICLR. They kind of use, plug into GAN something like the Fourier, basically amplitude and phase information, and they use the GAN basically to create some sort of latent generator representation that is able now to resynthesize. So a lot of their discussion in the paper is really to show that this is more efficient than other methods. So this is not the only way to resynthesize really from poorly structured spectrogram. We have seen, of course, methods for phase reconstruction in the class. So you can think about this as learning its own way of reconstructing sound. They compare this to WaveNet and other methods of basically vocoding or generating from some kind of a representation into sound. But also they can interpolate now. And again, this is one typical use of these latent representations. And again, it doesn't have to be VAE. It doesn't have to be RNN VAE. It could be latent representation learned by GAN. So this whole idea of improvising or playing, generating music or sound by manipulating or playing around in the latent space, I think is kind of an underlying common thread through a lot of these generative models. So here's an example of them trying basically to use, so this is a musical piece with one timbre, and then they basically can interpolate and change the sound. So this is sound synthesis example. I'll play this and I will have pretty much to end. So let me make sure that I'm, okay, I hope I shared, oh, I don't know if I'm sharing this one. I guess I'm not. Okay, you should have shouted and told me. So this is the GANs paper. This is the example I was going to show. Check out the links. So here's the consistent timbre. Just let me see if I'm doing the sharing with sound. Yes. So this is the original. So this is synthesized, but this is synthesized with one timbre. And now, because of this generative modeling, they can also go and change from one representation to another one and get this piece slowly shifting in timbre. think, hopefully I convince you that there is some kind of an interesting transition in terms of the type of musical instrument, and this is not something you can easily accomplish if you just, on the synthesizer suddenly switch an instrument, or with the recording that you start crossfading, that becomes, of course, another. You can maybe manually emulate this thing, but you don't have a mechanism that kind of smoothly moves and creates this intermediate timbres. We can think about lots of other applications and interpolations, creating new voices. Just a little anecdote, and then I'll basically have to run. For instance, there was a big project down in IRCAM. That's a place that I've been collaborating a lot. So this was kind of 20 years ago, and they had a film called Farinelli, which was supposed to, which is a film, and I don't know if you can find it on Netflix, but it's about the castrati. Castrati were singers, male singers that were castrated in order to maintain like a childish voice, and it was considered like this divine voice. So there was a film about this Farinelli, this castrati, and they wanted to create this imaginary voice that doesn't exist. So what the team that I was working with was doing was really, they had two soundtracks. They had all the vocal performances, because a lot of this is music and operas, and performed once by a male singer, once by a female singer. They had to align these tracks together and do much more detailed analysis than FFT, but do like a sinusoidal analysis, and then somehow interpolate frame by frame to create this imaginary voice, which is a blend of male and female, kind of to recreate this non-existent voice. So given these models, I think that would have been much less manually laborious work. But you can think about creating like sound effects for games where you want to have a new, totally imaginary bird call that is interpolated between a Land Rover and maybe a penguin. I have no idea. I'm just kind of going wild with speculations. But this is one thing, really, being able to generate for speech. Yes, I mean, if you think about emulating speech synthesis, creating cloning voices, then even without the need to create like a fake voice, even just being able to generate expressive inflections in the voice by synthesis. This is definitely a field where generative models are very powerful, and there are many other models it's like this. Okay, I stop my sharing here, and